Alright, so in 7.2, I just want to touch base on an alternate acid-base theory. Sometimes we call this the Bronsted-Lowry acid-base theory. The Regents generally has been using the terms alternate acid-base theory. We talked about in 7.1 notes the Arrhenius definition of an acid and a base, and I mentioned that there are other definitions of acids and bases. So we're going to look at that one a little bit closer on this slide. All right, let's take a green, actually let's take a pointer, because the pointer wasn't working very well in the last video, but hopefully it works better here. In this definition, let's look at acids first. They are proton donors. That means they're going to give away a hydrogen ion. And when I say protons, I am basically talking about an H plus ion. That's also known as, aka, a proton. So hydrogen ions are protons. If I give away or donate a hydrogen ion, then I am a Bronsted-Lowry acid. So it's very similar to the Arrhenius definition, which said if I give away an H+, I'm going to be an acid. The Bronsted-Lowry also says if I donate an H+, I'm sorry, they're hanging a fan upstairs, you can hear them banging. If I donate a hydrogen ion in solution, then I'm going to be an acid. So generally the same thing. But this accounts for the fact that we have these organic acids right here. Hopefully you can see it. And it starts with the CH. That's making it organic. But it ends with this COOH group. And that COOH group is called a carboxyl group. And that carboxyl group has a hydrogen that hangs off the end, and that hydrogen that's hanging off the end there can be given away. So this CH3COOH is actually an organic acid. It donates that hydrogen, and that hydrogen, when it's donated, makes this an organic acid. Okay, now let's look at the Bronsted-Lowry or alternate acid-base theory for bases. This one is totally different because in the Arrhenius base, we noticed that it gave away an OH ion. But in the Bronsted-Lowry alternate acid-base theory, the bases are accepting a proton or taking an H+ ion. And this allows things that don't even have OH ions, like ammonia here that I just circled. There is no OH ion that they can donate. So if they accept an H+, they can also be considered a base. I'm going to write down here, let's see if I can do this without making a mess. Okay, I'm going to write the ammonia, NH3. There's no OH to donate, but if ammonia interacts with water, that ammonia can accept a hydrogen. So let's get a different color. Let's say this hydrogen, this water breaks into H pluses and OH minuses, right? If that H plus is donated from the water and is accepted by the NH3, that NH3 is going to become NH4 plus, and an OH ion is going to be left by itself. That's this OH ion right here. Let's see if I can find a highlighter. Okay, that OH ion is this OH ion. And so we have these OH ions that are floating around in solution, which makes it basic. But it is not a base because it donated that OH ion. It's a base because it accepted a hydrogen ion from the water. It pulled that hydrogen ion off the water. And what happens is this water, it's not a pen, this water is acting as a Bronsted-Lowry or alternate acid base, right? It's acting like an acid, and this ammonia is acting as the base because the ammonia is accepting, let's see if I can write that, an H+, and the acid is donating, that's a D, an H+. Okay? So now what I'm going to do is I'm going to try to zoom back in here and see if this works. Okay, didn't really work very well. Hold on, let me come back. All right, so I tried to zoom in the best I can. Hopefully you can see it. You've got this ammonia that's going to be accepting the hydrogen. This is not water, it's H2SO4, which is going to act like the acid because that H is going to go over to this ammonia, and you're going to end up with SO4 minus 2. You can see that over here because it lost its H, and this NH4 gained it. So now the base, which is ammonia, and the acid, which was the HSO4, became NH4 plus and SO4 minus 2. Now in this type of acid-base reaction, we deal with something called conjugate acid-base pairs. In other words, if you have a base like ammonia, let's get a pointer so you can see what I'm talking about. Hopefully it's lined up. If you have that ammonia, which is a base when it accepted, over here the ammonium, because it became ammonium, right? It gained a hydrogen ion. That ammonium is acting like the acid. So this acid and this base are considered acid-base pairs. They're a pair because that acid has one more hydrogen than this base. Always, when you are looking at or looking for conjugate acid-base pairs, the acid will always have one more hydrogen than the base. And so what I like to do is let's get an eraser here. What I like to do is red, join the ones that are most similar to each other. The ammonia and the ammonium are most similar. They differ by only one hydrogen. And the HSO4 and the SO4 are most similar because they differ by one hydrogen. And you'll always remember, oh, here, look, differ in only one hydrogen. The acids in the pair will always have more hydrogens, okay? So the HSO4 and the SO4 minus 2 are a pair. They only differ by one hydrogen. And the one that is the acid in that pair always has one more hydrogen. And so this one's going to be a base, and this one's going to be a base. So those are conjugate acid-base pairs. Let's try, I'm going to go to a different slide and we'll try one together. Oh, while I was away, I learned how to flip the frame so that I have more space to write. Okay, let's see. Let's do HCl plus H2O yields H3O plus and Cl minus. And let's see if we can find the conjugate acid-base pairs. So I'm gonna go HCl and find the one that's most similar to it, that's differing by only one hydrogen. And so those two differ by only one hydrogen. And this H3O and this H2O are very similar. They're only differing by one hydrogen. Okay, now we're going to figure out which one's the acid and which one's the base in the pair. The HCl has more hydrogens than the Cl, so these are the two I'm looking at, this one and this one. Which one is the acid? The acid will always have more hydrogens, so this is the acid and this is the base in that acid-base pair. We call that a conjugate acid-base pair. And then when we look at the other two, I'll change the color to green, these guys differ. Oops. This one and this one differ by only one hydrogen. Which one is the acid? The acid is going to be the one with one more hydrogen, and this one's going to be the base. Those are called conjugate acid-base pairs. Okay, so hopefully that made some sense, and until next time,